Elon Musk just made a call that risked the entire mission. 9 days before splashdown, 4 engines failed to ignite. 33 engines, 4 refused to fire. Musk ordered them ripped out and replaced in 5 days flat. Then he sent it back to the pad. So did the fix hold? Did Starship actually make it? Stay with me. You need to see how this ends. July 16th, 5:45 p.m. Texas time. 33 Raptor engines, 1 countdown, and then nothing. The clock hit 0, ignition started. On the live telemetry screen, something was wrong. 4 engines out of 33 simply did not light. Not a delay, not a hold, a hard abort at the exact moment of ignition. The most powerful rocket ever built, fully fueled on the pad, shut itself down in real time because its own systems caught a problem before the humans did. 33 engines is more than any rocket in history has flown with. The Soviet N-1, the only other rocket that tried a similar count, failed on all 4 of its launch attempts. 3 of those 4 failures were engine problems. So when 4 engines refuse to ignite on a modern 33 engine booster, that's not a footnote. That's the exact failure mode that has haunted every vehicle that ever tried this approach. SpaceX confirmed it within hours. The launch was scrubbed. Starship, the tallest rocket on the planet, came back down off the pad. What actually went wrong? An engine didn't light sounds simple. It isn't. Each Raptor engine on Super Heavy ignites in a staggered sequence, not all at once. If all 33 fired simultaneously, the shockwave and thermal stress at the base of the booster would be catastrophic. So they light in a carefully timed pattern, milliseconds apart, while a water-cooled flame diverter beneath the pad absorbs the heat and vibration. Picture that sequence as a chain of dominoes, except each one has to fall at the right microsecond under extreme heat, with liquid methane and liquid oxygen running through it at pressures most industrial systems never touch. If one domino is even slightly out of position or reading the wrong sensor data, the safety system halts everything downstream. That's what happened here. 4 dominoes didn't fall the way they were supposed to. This wasn't the first sign of trouble in this engine family. 2 months earlier, on Flight 12 in May, a startup timing issue threw off the booster's separation flip by roughly 90 degrees. 5 of the 33 sea-level engines had problems during the boost back burn. That booster, B19, was lost. It never made it back for a controlled landing. So when 4 engines failed to ignite on July 16th, everyone watching had the same question. Was this the same failure again? Or worse, was Starship about to repeat its worst outcome twice in a row? Here's a number worth sitting with. NASA's Saturn V, the rocket that took astronauts to the moon, flew with 5 engines on its first stage and experienced 1 engine-out event in its entire flight history during Apollo 13. Super Heavy runs 6.5 times that engine count. More engines means more thrust and more built-in redundancy. It also means more chances for something to go wrong in that same half-second window where it matters most. Musk didn't wait to respond. Within the day, he confirmed publicly that at least 2 Raptor engines needed to come off the booster following what SpaceX called a hard engine stop, a fault severe enough to kill ignition instantly, with no gradual shutdown. Less than 24 hours after the scrub, Ship 40 was destacked from Booster 20. The booster rolled nearly 3 miles back to the production site at walking pace, past the same workers who'd watched it fail to launch the day before. For a full week, teams pulled engines, tested them, replaced what needed replacing. Technicians in Texas heat, removing half-ton components from a booster over 200 feet tall, racing a schedule the whole industry was watching. By July 21st, Booster 20 rolled back to the pad. The next day, SpaceX loaded it with liquid oxygen and liquid methane, then drained it again just to confirm the fix held under real cryogenic conditions. Every hour, Booster 20 sat in the shop cost schedule time on a program already facing outside scrutiny. But clearing an engine that wasn't actually fixed didn't just risk a booster. It risked the full stack on a live broadcast in front of regulators who already require a formal investigation for far smaller incidents. That was the tightrope. Move fast enough to hold the date, careful enough not to repeat July 16th in a worse form on the next attempt. Weather doesn't care about your schedule. Just as the hardware was ready, Tropical Storm Bertha pushed through southern Texas. SpaceX waved off the next attempt entirely, pushing the flight from July 23rd to July 24th. No amount of engine expertise changes wind shear. No static fire test moves a storm path. One team, 1 week of round-the-clock repair work, stopped cold by something no engineer could control. Friday, July 24th, 5:51 p.m. Central Time. Same booster, same 33 engines. Updated alarms, modified hardware, built specifically to prevent a repeat of July 16th. The countdown reached 0. This time, it didn't stop. All 33 engines ignited. The vehicle cleared the tower and powered through max Q, higher stress on this flight than any previous Starship mission, a result of the larger version 3 airframe. Minutes later came hot staging. The ship's 6 engines ignite while still attached to the booster, shutting down all but 5 of the booster's engines in the same instant, one of the most violent moments in the entire flight by design. Then came the maneuver that mattered most, the boost back burn. The same maneuver that failed on Flight 12. The one that, if it failed again, meant Booster 20 joins Booster 19 at the bottom of the Gulf. It worked. Booster 20 made a controlled landing offshore in the Gulf of Mexico. No crash, no engines lost mid-descent. The exact outcome that eluded its predecessor 2 months earlier. Flight 12. 5 engines failed during boost back. The flip was off by 90 degrees. The booster was lost. Flight 13. Rebuilt engine alarm thresholds, targeted hardware changes, a clean water landing. Not luck. SpaceX's own review tied the loss of B19 to heat damage in the propulsion system combined with what the company called erroneous engine alarm settings. The booster's own safety software misreading real conditions as a fault. Fixing that meant rewriting how the vehicle interprets its sensors under multi-engine stress, then proving it in the harshest test available. An actual flight, live, no second attempt if it failed again. Meanwhile, on the other side of the planet, Ship 40 was writing its own chapter. The payload. Nobody was talking about. While the internet fixated on the booster, Ship 40 carried something SpaceX had never flown before. 20 production Starlink version, 3 satellites, not simulators. Actual, functional hardware. Each V3 satellite handles roughly 1 terabit per second of downlink capacity. A single flight carrying a full load delivers something like 20 times the network capacity of one Falcon 9 launch carrying the older V2 satellites. 6 of the 20 carried cameras, positioned to inspect Ship 40's heat shield in flight, a technique borrowed from the Space Shuttle program's rendezvous pitch maneuver, where a spacecraft rotates in front of an observer so every surface can be checked before the riskiest phase of the mission. NASA used it after the Columbia disaster. SpaceX adapted the same logic here, using satellites it was deploying anyway as inspection cameras on their way out. The satellites weren't kept. Designed to burn up on re-entry roughly 20 minutes after deployment on the same suborbital path as the ship itself, purely to prove the process before production satellites joined the real constellation. The heat shield under inspection wasn't the same design as previous flights either. SpaceX tested multiple tile attachment methods side by side in one flight instead of spreading the tests across several missions. Some tiles bonded directly to the metallic aft flaps. Others used modified mechanisms around the aft skirt, the section taking the heaviest heat load on re-entry. Some carried load sensing instruments, measuring real stress as the ship pushed through higher dynamic pressure than any previous flight, a trade-off accepted in exchange for more payload capacity down the line. This flight was quietly running several engineering experiments at once, graded in real time by 6 satellites acting as flying cameras. Why this flight matters far beyond one booster. This exact version 3 vehicle is the version SpaceX plans to use for Artemis 3, NASA's mission to land astronauts back on the moon, with a nearly identical Starship set to dock directly with NASA's Orion spacecraft in low Earth orbit. Which is why a Government Accountability Office report, published the same week as this flight, carries extra weight. It states SpaceX is more than a year behind schedule on key human landing system milestones, including the critical design review and an uncrewed landing demonstration, and it names continued Raptor engine development a top risk to the entire lunar timeline. Set that against what just happened at Starbase. The same engine family that forced a scrub, a 5-day emergency repair, and a full alarm redesign is the engine NASA is counting on to help land Americans on the moon by 2028. The report does credit one fix. The latest Raptor includes welded fuel joints designed to prevent the fuel leaks that caused a Starship loss in March of 2025. Flight 12 was the first test of that update. Flight 13 was the second. 2 data points. 1 successful splashdown after 1 very public failure. So here's the real question. Is a 5-day repair and a clean splashdown proof SpaceX has solved its multi-engine reliability problem for good? Or is it one good result inside a program NASA's own auditors are calling a top risk to a 2028 moon landing? Booster 20 came home. Ship 40 splashed down on the other side of the world. 20 Starlink V3 3 satellites proved a deployment sequence the whole industry will be watching. And somewhere in Texas right now, engineers are already staring at this flight's data, working on the one answer that decides whether humans walk on the moon again by the end of this decade. That's the data. One failure, one fix, one splashdown. I'm Adrian, the Space Brief. If this analysis helped, like, subscribe, and share your take below. More breakdowns on screen. Thanks for watching.